So let's see what are the axes of symmetry of the polygons depending on the parity of the number of vertices that they have. So if I have a pentagon, for example, so pentagon has an odd number, that is it's supposed to be regular, so all the sides and angles are the same. This is a situation analogous to the equilateral triangle, which also had an odd number of vertices. Then the axes of symmetry are always connected to vertices. So it's always the vertices. They go through various vertices and they drop perpendicularly onto the opposing side. If you have a, say, for example, a hexagon, so an even one, that's a situation like in case of a square. It's a regular hexagon. And then you have two different types of axes of symmetry. Those that connect vertices, they'll give you three axes of symmetry. And then those that connect the midpoints of opposing sides. Maybe I should use a different color here. So you get the ones that connect midpoints of opposing sides. In any case, you have n axes of symmetry, right? So five axes of symmetry. And 6 axes of symmetry. The axes have different nature, but nevertheless, there's as many of them as you have vertices in your regular polygon. So a dihedral group, or how about this? So for each n, we get the group of symmetries of a regular n-sided polygon under composition this group has 2n elements and is called the dihedral group of order 2n, denoted by d sub 2n. D6 for an equilateral triangle, D8 for a square, D10 for a regular pentagon, D12 for the regular hexagon, and so on. And it always consists of elements, half of which are rotations. If you think about the do nothing, it's also a rotation by 0 degrees. And half of them are flips with respect to these axes. And I encourage you to play with them a little bit. So for example, take pentagon and try to compose these in different orders and see what you get.